bother do it in sixth period because everybody said they did it. And I just didn't feel like checking their math. But I'm nervous here after seeing what I just saw when I walked around real quick. If that's the edge and I have 10 different individual point masses, I'm doing the sum of each point mass and its distance away from the reference point divided by the entire sum of all the mass pieces. Right? So I'm going to have 10 things in my summation. Thing number 1 is going to be 10 grams. Each piece is 10 grams, and it is located let's do it all in centimeters. That'll be easiest for you. It is located 5 centimeters away from the edge, right? I've handled dot number 1. Ready to go on to dot number 2? Dot number 2, how big is it? 10 grams. Okay, excellent. And how far away from the edge is it? Wow. It is 15 centimeters away. In my head, I keep thinking I was going to divide, but no, 15 centimeters away. Right? It's 10 centimeters between dots. The first one is 5 centimeters away from the edge. I am beginning to see a pattern, but perhaps you're not. We have 8 more of these to go. So 10, and the next one is going to be, where's the next one going to be? 25, that's right. 10 more centimeters. I think I see enough to understand the pattern. I also know that every one of these is going to have a 10 in it, isn't it? So maybe, if I was actually going to do the math, I could just take the 10 out front and do 5 plus 15 plus 25 plus 35 plus 45 plus 55 plus 65 plus 75. Oh, how do I do it? Do I need to count how many of these there are? Or do you know where to stop? Because, I'm not trying to be a jerk, but you'll need to stop at the right location, which better be less than a meter, right? All divided by the whole mass, 100. 95 and 5 is 100. 85 and 15 is 100. There might be some interesting interplay between these numbers. Perhaps. Do you see what I'm seeing? Are you able to sense the pattern? I know some of you, I see yes, but some of you I see that look on the face of let me not say it out loud. But that's 100, that's 100, that's 100, that's 100, and that's 100. How many hundreds are there? 5. So I have 10 times 500 divided by 100, which is 50. The center of mass of a 100 centimeter ruler is at the 50 centimeter mark. Duh. Now, why? Well, remember, as accurate as this is, the truth is, it's not perfectly accurate. We are assuming that the extension allows us to estimate. Now, when I say estimate, these aren't point masses, right? The meter stick has extension. So we are using an estimate. Now, we got the center. I nailed it, actually. It's 50. Way to go. Of course, we could break it up into 100 pieces to get a more accurate representation, but that would just give us 50 again. Now, in 3 weeks, when we do moment of inertia, we will do this again. But moment of inertia isn't the sum of mi times ri. Moment of inertia is mi times ri squared, making the actual distance away from the reference point more important. This will lead to problems and will also mean that our answers are going to no longer be perfect. They're not going to work out to be exactly what we expect. They're going to be an estimation. I'm using center of mass now to teach how to do the math here, because there's some parts of this that are easy. Obviously, this was easy, but also sometimes the extension makes a difference. Where I'm going with this is, what if each piece didn't add the same weight each time? What if each of these dots was a different mass? If you're wondering what I'm talking about, an example that maybe looks like this. Let's see if I can do this right. What if my meter stick looked like this? This meter stick has clearly a non-uniform mass ratio. Do you see why that's true? If I was to break it up into 10 pieces, the pieces at this end would have less mass than the pieces at this end. Now, based on its shape, there's probably a pattern to how those masses increase with each piece. Bless you. But you understand that each piece is going to have more mass than the piece before it. This will no longer have a center of mass at the middle. And breaking up into pieces is likely only going to be an estimate of where the center of mass is. The extension now matters. There has to be other math to do this. And there is. There's other math to do something like this, where our object's shape now begins to create a role in how you would do the center of mass calculation. Now, I want to teach you how to do this, but it is well beyond the scope of your calculus class. Those of you who are in E&M, we've done this already. But those of you who are just in AB, I want you to understand, even the folks in BC have not been taught how to do this. This isn't taught in calculus. But when we say that calculus is required in physics, sometimes the calculus you have to be taught isn't taught in a calculus class, it's taught in a physics class. And this is the case of where it is. This would probably be taught now in Calculus 3. I think that's where they've moved it to in most college campuses. So we're going to have to learn how to do this, though. This is in our curriculum. Now, usually I wait until we get into moment of inertia and only teach this at moment of inertia. But I've decided to teach it during center of mass because center of mass has some simplifications that make learning how to do this a little easier. So what we're going to do is we're going to go back to our meter stick example, and we're going to talk about a generic meter stick. When I say generic, it's got mass M, and its length is length L. Generic. It is a uniform rod of uniform mass density. Okay? I want to teach you how to find the center of mass of a object of uniform density. It's on the equation sheet, so I guess once you have the equation, you can do it, right? And what's on the equation sheet looks like this. Obviously very similar to what we did already. Similar. This one assumes point masses or individual pieces of mass that can be separated and identified. This assumes a smooth object of uniform density. Actually, not even of uniform density, just a continuous object. It doesn't have to be of uniform density. Now, I'm going to hit the pause. Yeah, I know it's mathy and I get it, but I'm okay with it. I like doing math stuff. It makes me feel superior. You guys should try it sometimes. Try and feel superior. It's fun. The symbology is not particular. I'm going to try and find a way to create a summation, but a summation that uses calculus to find the answer, which is why we're going to do this. We're going to do the summation side, but we're going to do the integral as our summation. So all that stuff that you're learning in calculus, or will learn when you take it next year, is in the hopes that when you're faced with a situation where you have to take the integral, you have a tool set of how to do an integral. Unfortunately for us, the hard part of this isn't actually doing the integral. The hard part is setting up the integral. That's actually really hard because of what this actually is. So what I want to do today is I want to teach you how to set up this integral. You already know how to do the integral. I taught you that back in September. So we're going to talk about how to set up the integral. I had to erase the L, not because I don't want it there, but because it's going to be distracting. So we're going to say that this object has length L and mass M, and I'm going to put that off to the side. Okay? And for the time being, I want to focus on the top part of this fraction because we already know the answer to the bottom part of this fraction. The bottom part of this fraction says, break your object up into small pieces, dm, and add up all the pieces. So we already know the answer to this is m. The sum of all the pieces of mass is the mass. I have to say pieces of mass a lot today. I will try not to slip up. So the first thing I want you to do, and I should write this down as a series of steps, and I did a little bit in sixth period, but then I stopped because I started to hustle. So step 1, I would encourage you to write these down. Step 1, on your diagram, indicate a piece of mass. Draw a box that is your fictional piece of mass. For me, what I really am asking you to do is identify a box. I am drawing a physical box on my object. Now, to me, our object has clear one-dimensional symmetry, right? It looks one-dimensional. It's very long compared to any other measurement of the object. So I also have to, and I call this step 0 if I really could, is does your object have some kind of symmetry that you can exploit? Is it one-dimensional? Is it two-dimensional? Is it three-dimensional? I think we could all agree a meter stick is one-dimensional, right? Now, if you had going back here, we indicate that. Now, these next two sound like they're not important, but they're exceptionally important. So step 2 is identify your reference point. Identify your reference point. I'm going to put 0, but identify your reference point. You will sometimes be told the reference to use. Sometimes you'll be told. You'll just have to use it. For a moment of inertia, you're going to be told the reference to use. So center of mass, though, we get to pick our reference point. I think it's obvious, but I'm going to choose the end as the reference point. Step 3 is tough, I think, until you realize it's just asking you what kind of coordinate system you're using. I don't say it like that, but that's what it is. R is a placeholder. It was a placeholder in the summation formula too. It says, where is your piece? Now, for us, we're going to be specific. We're going to be replacing R with something we can use to point to our object, and we are choosing a coordinate system that makes sense to do so. Our object is on a frickin' number line. So I'm going to say that my piece is located a distance x away from 0. It's a number line. So using a single value to represent where it is makes perfect sense. Step 4. Once you have decided what variable you're going to use to point to your object, this next one's weird, and I get that it's going to be tough, but you need to describe its size. Describe the size of the box using your chosen variables. Boy, I'm still writing all those out. Describe the size of the box using your chosen variables. Now, this one seems weird, but my box has linear symmetry. I'm going to describe the length of the box. If my box was two-dimensional, I would describe the area of the box. If the box was three-dimensional, I would describe the volume of the box. Does everybody understand? So with one-dimensional symmetry, my description of the size of the box is how wide it is. It is dx wide. dm means a small piece of mass. We have identified dm as a piece of the mass. So we are going to use a calculus descriptor to describe the length of this mass. So we use dx. dx means a piece of length. If dm is a piece of mass, dx is a piece of length. But not just any piece, it's a piece in the x direction. Okay, we've done a lot of heavy lifting now. This next part is kind of an aside, and we got 7 minutes, so I want to make it work. We want to find a relationship between dm and dx, meaning dm and dx are related. Now, this would be mass per length. Do you know any measurements you've had in science that sound like mass per length? Let's generalize it. Mass per size. Density, that's right. Density is a relationship between the mass and the size, how much space the object takes up. You've probably learned about one kind of density, volumetric density, mass per unit volume. That's chemistry, right? But there's lots of different densities. Who's in the orchestra? Nobody. I guess orchestra must be 7th period. Who's ever seen a stringed instrument? Have you noticed that some strings are thicker than others? So they must sell strings for stringed instruments based on their mass per unit length, right? The length density. So there's a name for that, mass per unit length is called linear density. And there's a symbol associated with it, and for this, you do need to know the symbol. It is lambda, lowercase lambda. It's about the size of an h, a lowercase h. That's how you should treat it. Has anybody ever shopped for paper before? Have you ever noticed that there's some paper that is thicker than other paper? Like, there's the paper that's like cardstock. That's nice stuff. That's the good stuff. But then there's paper like tissue paper that's really thin. You know where I'm going with this, right? That there's got to be a mass per unit area measurement. And of course, that would be area density. Toilet paper, I would like it to have a thicker area density, but not the stuff they have here at the school. They don't. That's really not great area density, is it? The stuff here at school. You got to layer up with that stuff. So that a good analogy? And of course, you already know about volumetric density. There are symbols for all of these that are accepted in the use of this class. We will probably not use area density. In fact, we might not use lambda very much, but lambda is something you're supposed to know. Lambda stands for linear density. The sigma stands for area density, and rho stands for volumetric density, but I don't use them very much. Now, our object has uniform density. That's an important phrase. So we already know the density of our object, the linear density, because our object has mass m, length L. That's got to be the linear density of our object. We were told the object has mass m and length L. And since every piece of the object has to be the same density, that has to equal dm over dx. We have a choice here. You could write this as dm equals lambda dx, or you could write this as dm equals m over L dx. I don't care which, but they could give you something that has non-uniform linear density, and they might give you an equation for lambda. This is why it's important to probably see both forms. But based on how much time I have, I'm going to just use the bottom one because it'll be faster. Now, all of this, and I stopped counting steps here, but 5 was dealing with density. All of this was to produce an alternative to dm. Our goal is to come up with something to use for dm that can describe the mass of an object based on its shape. And that's what we have. A description of the mass of the object based on the size of each piece, its shape. So we have transformed dm into dx. So our integral now starts with our summation system. R is a generic pointer. I said that at the beginning. We are pointing to our object with x. So I will replace R with x. dm is a generic term that indicates a piece of the mass. We will now replace it with something that is related to the piece of the mass and its shape. That's going to be m over L times dx. We have one thing left to do. We need to tell the integral, just like we told the summation, where is the first object and where is the last object. It's going to automatically know how to count them. The first object is located at 0. We're using x for this. So our first object is based on where the first mass is. And our last object is located at the end of the rod, L. We will integrate each piece of mass, starting with the piece closest to 0, all the way to the piece at the end. Now, you know how to do this. M and L are constants. They would be the same for every term in the summation. They can be pulled out front. You have done this in this class before. X is a polynomial. That is x to the 1 power. So, antiderivative, x to the 1 plus 1, divide by my new exponent, 1 plus 1. Make sure to put in my limits of integration, 0 and L. And don't forget that I am multiplying each term by m over L. No surprises there, right? We've done this part before. I feel confident even all of you pre-calc kids have done this before. And we talked about what to do next. Put in the top boundary and subtract the bottom boundary. So this will be m over L times L squared divided by 2 minus 0 squared divided by 2. Am I doing okay? Oh, come on, just give me 15 seconds. That is m L squared over L times 2. Can we cancel the L's? M L over 2. Now, this is the top part of the fraction. Where is the center of mass? The bottom part is the integral of just dm. What is that again? What is the sum of every piece of mass for a whole object? It's mass. That's right. It's just m. Can you do this algebra real quick? Can we cancel the m's out? Where's the center of an object? At its middle. I know. A lot to just get 50 centimeters again. All right. I hope this was a value. I had a piece of wood like this. I wouldn't say that this is one-dimensional. For this, we might have to find a piece of it somewhere out in the middle. And you would identify a piece. That's okay. We're still going to do the same thing. In a two-dimensional system, we would still have to identify a piece of it. In a three-dimensional system, we would identify a piece of it. Everybody okay so far? This looks boxy, doesn't it? So I'd probably use Cartesian coordinates because Cartesian is boxy, right? I could use X to find out how far along the horizontal this piece is, and then use Y to figure out how high it is above the horizontal. I would probably use Cartesian. I probably would not use polar, right? Because there's not symmetry with polar, but there'd be symmetry with Cartesian. I know where the beginning is. I know where the end is in all directions. That makes perfect sense, Cartesian. If something is boxy looking, use Cartesian. If something is circular, probably use polar. I would describe this piece differently, because this piece has, obviously a dy component, how tall it is, and it has a dx component, how wide it is. So I wouldn't describe its length or its width by itself. I would describe a piece of area, which would be length times width. That's how I would describe the area of the box. This symbol means to add up. We often leave out parts of it. Like me writing this is enough for me. But what it's supposed to be is that, okay, there is an individual group of objects, all with their own mass, and they're all located somewhere. R represents where they're located. M represents the individual pieces of mass. Right? That's what this, now, this could be anything. Like if I wrote the sum of A times Ri, then obviously A is multiplied by every object that's located at R. And it's the same. I didn't put the little I subscript on it, which means the A's are all the same. It's the same coefficient. I could probably just pull it out front because there's going to be one in every term. You follow so far? And this is why the difference between whether the R can come out or not depends on whether R is the same for every object or not the same for every object. And that's what we'll talk about in a moment. But here, if I put the I subscript on it, I am specifically saying that each object has a different value for its mass and is located in a different place. So I'm supposed to say, okay, I want to start by starting with object number, oh wait, not I. Well, yeah, no, I'm going to use I as my counter. So yeah, so I'm going to start at object number 1. And how far are you going to go? Well, I'm going to go until the last object, which is object number n. I don't know how many objects there might be. Now, if I know there's 10 objects, and the thing we did before, there is a way to write what we did before for the meter stick. Do you guys understand that? There's a recursive way to write it. Now, I don't know if you guys have done recursive equations before, where you looked at summations, found a pattern, and found a way to write the recursive notation as a recursive equation. Did you guys do any of that? I don't know if it's taught anymore. There's real power in it, but I'm afraid that school doesn't have time to teach that kind of stuff. Recursive equations do what we did. You saw, right? We were adding 5 plus 15 plus 25 plus 35 plus 45. There's a way to write that as an equation. It would be 5 plus 10 to the n. Right? And I would add that up from n equals 0 to n equals, what was the last piece, 10? No, 9, because I had part 0, so 10 equals 9. This would have been it. So, all right. The reason why I need you to understand this is because of its implications to that. The difference between these two is that we're no longer going to deal with individual pieces. We're going to assume that we're breaking this uniform object, I keep saying the word uniform, this continuous object up into many small pieces. The integral allows us to break it up into an infinite number of pieces. That's a trick of the math. It's not really an infinite number of pieces. We're using the principal equation for calculus, or whatever it's called. What's that? The thing they taught you in the first couple of months? The fundamental equation for calculus. You're using that to estimate what it would be like to break this up into an infinite number of pieces. So when we go back